what makes implicit differentiation tricky is that you have to use the derivative chain rule, and you have to kind of, I don't know, it's a different perspective on things. So far this semester, we've only been dealing with explicitly defined functions. And what it means to be an explicitly defined function is that like one side of the equation is just y, my output variable, by itself, plain old y. On the other side of the equation, we have a function of only x. There's only one single variable x on the right side of the equation. It might be x squared, it might be sine of x, it might be something really complicated, but there's only ever x's. The difficult part of implicitly defined relations is that you could have an equation where there's kind of a combinations of x and y's on the left side and the right side, and it can get messy to the point where you can't detangle it. You can't separate the x's and the y's from each other. But we can still take derivatives of these equations. And when we take a derivative of this equation, the strategy is called implicit differentiation. So we're not going to rewrite it as an explicit function. We're going to take the derivative of the equation as it is. And so if I'm looking at this, x squared plus y squared equals 1, and I want to take the derivative of both sides with respect to x, what would that look like? The derivative of x squared would be 2x. And what I'm about to write down next might sound a little crazy, but this is going to be 2y times dy dx. And the derivative of 1 is 0. Good morning. So this is the new part, right? And I have to explain what's happening here.
You said it's multiplied by dy over dx?
Yeah, that's 2 times y times dy dx. What's happening right here is we say y is a function of x. Or at least we could say that y and x are related in a way so that if I am concerned with taking the derivative with respect to x of y, there's something there. There's a ratio of the changes of these variables. So whenever I see y squared, think of the derivative chain rule. And the derivative chain rule says this. We take the derivative of the outside function first. And the outside function here is y squared. The derivative of y squared would be 2y, right? Then we multiply times the derivative of the inside function. What's the inside function? It's y. So when I multiply by the derivative of y, I write dy dx because dy dx is the Leibniz notation for the derivative of y with respect to x. So it's a weird way to apply the derivative chain rule. And my question now says, find dy dx using implicit differentiation. Well, we've already used the implicit differentiation part. Now to find dy dx, I just need to subtract 2x from both sides. And then divide both sides by 2y. And it turns out the dy dx, which means the derivative of y with respect to x, that we find with implicit differentiation is negative x over y. A lot of times when you use implicit differentiation, the derivative you come up with is not just a function of x, but it's a function of x and y. That's not unusual. Any questions about this? We can do more examples, but any questions about this one? Yeah. All right. Another question I can ask is find the value of the derivative where x is equal to a particular value and y is equal to a particular value. Like this time x is equal to -1/2 and y is equal to square root 3/2. And we have already used implicit differentiation in the previous example and found that dy dx is equal to -x/y. But this time, if I say x is -1/2 and y is square root 3/2, then now we're talking about the derivative here being -1/2 over square root 3/2. Two negatives make a positive, and so that's positive 1 over the square root of 3 for my derivative. You could also write like square root 3/3 if you really want to, but you don't have to. So something like exercise 2 is just a matter of taking the x and y values and plugging them into the function. And what if, I think on your homework, I took it one step further, okay? On your homework, I think I only give you an x value on the exercise 2 of your homework. And so the question now is, what if you're not given a y value? And it says, find the value of this derivative where x is equal to -1/2. Well, then what you would need to do is take a look at this original equation, combine this with the idea that x is equal to -1/2, and see what we get. That would be -1/2 squared plus y squared equals 1. -1/2 squared is what? 1/4. Subtract 1/4 from both sides, and then take the square root of both sides. And so there's two possible y values that work here, right? One of them is positive square root 3/2, and the other one is negative square root 3/2. And the way I worded this problem in my lecture notes, is that y was equal to positive square root 3/2. And that was one of the answers. But, if I don't give you the y value, if I only give you the x value, then it would be up to you to find the y value using the original equation, and then plugging it in and finding that there. Okay. Questions about this?
For exercise 2, we would have two different answers. Like, would we have one answer as 1 over square root 3, and then we'd also have the derivative of -1 over square root 3 then?
Mm-hmm.
Okay.
Yeah, so whenever y is positive square root 3/2, the derivative is positive 1 over square root 3. But if we use the negative version, then you'd have the same derivative but negative, right? You're right. Yeah, you'll get two different answers depending on what you use. And this next question might sort of help clear up what exactly we're doing here. I think it's going to make more sense after we see this exercise 3. It says, find the slope-intercept form of the tangent line. And the tangent line is just the line where the slope is the derivative. The slope of the tangent line will be the derivative of your function, or dy dx in this case. To the curve where, and you're given an x and a y value, Again, maybe you're not given a y value, but you could find it. And let's see what happens. It's the same original equation. And so we still know, like we did in the last example, that here at this point dy dx is equal to 1 over square root 3. At this point. And so that's going to be the slope of my tangent line. And to start, we should use the point slope form of a line. And then we'll rearrange it to get the slope intercept form. But it's your starting point is the point slope form. And for this point slope form, I can use this x and this y as the point that belongs to my line. 1 over square root 3 as my slope. And there we go. So that's everything plugged in. Let's simplify this by distributing the 1 over square root 3 to x, and I get 1 over square root 3 times x plus 1/2, so that's going to be 1 over 2 square root 3. And write that down, 1 over 2 square root 3. And then I'm also going to add square root 3 over 2 to both sides. You know, this is why it's potentially useful to, what do you call it? Rationalize the denominator. And in other words, write 1 over square root 3 as square root 3 over 3. And here we would want to write 1 over 2 square root 3 as square root 3 over 6. Because now I can add these fractions together. Because square root 3 over 2 would be the same thing as 3 square root 3 over 6. Multiply top and bottom by 3. And square root 3 plus 3 square root 3 would be 4 square root 3. And 4 square root 3 over 6 is the same thing as 2 square root 3 over 3. So that is going to be my final answer of the slope-intercept form of the tangent line to the curve at that point. So let's take a look and see how we did. When I plot x squared plus y squared equals 1 on Desmos, I get a circle. That's the circle x squared plus y squared equals 1. I'm concerned about the point on the circle where x is negative half and y is the square root of 3 divided by 2. That blue point. And I wanted to know what's the slope of the curve here, right? What's dy dx? That's the slope of this curve when you zoom in really close. And the slope was 1 over square root 3. Okay? What happens if instead of being concerned with this point at negative half for x and positive square root 3 over 2 for y, what if I took the negative value of y at the same point? You know, that's another place where this curve exists. If I didn't give you the y value, I only told you the x value is negative half. And there's 2 y values to choose from. There's this one and this one. So then you put a negative in front of the y value, and now we're talking about this point. And if we zoom in really close to this point, it's the same slope, but negative, right? It's like the same amount of steepness, but this time it's decreasing. So you got a negative. That was one of your questions, I think. is yeah, you get a different slope because you're talking about a different point on the curve. So you should expect to calculate a different dy dx when you choose a different y value. And then the last thing we did in that exercise number 3 is we found the tangent line was y equals square root 3 over 3 times x plus 2 square root 3 over 3, I think. And so that was the tangent line of the curve at that point. So this is not a function, right? If you remember your college algebra days, your pre-cal days, this red curve does not represent a function because it fails the vertical line test. Functions have to take one input value x and only give you one output value y. But this is not a function because it can take an input value x and potentially return 2 output values for y. So that means it's not a function. But even then, if you want to know the slope of a curve, even when defined implicitly, you can still do this with derivatives, like we just did. So, any questions so far? Any thoughts or concerns? Okay. Stop me, let me know. Raise your hand if you have a question. But that's it for today. That's the new stuff. We're going to keep working more examples, but that's the new concept that we're trying to work on. All right, find dy dx using implicit differentiation. Again, this is not a function where y is on the left side and on the right side of the equation we have just a function of x. This time my x's and my y's are all jumbled up. So this is a curve that's defined implicitly, but we can still take derivatives. So for this one, when I'm trying to take the derivative with respect to x of the entire equation, you can go term by term because of the derivative additivity rule. We can just go one term at a time and take derivatives. What's the derivative of y cubed? 3y squared times dy dx. Okay? And again, this is the tricky part that always got me as a student. Because you might ask, what the heck is going on here? Y is a function of x. So we have to think about the derivative chain rule. And the derivative chain rule says, first take the derivative of the outside function. The outside function is y cubed, so the derivative is 3y squared. And then multiply by the derivative of the inside function. And the inside function is y. Y is the inside function. The derivative of y is dy dx. So we're multiplying times dy dx because that's what the derivative chain rule says to do. So this part is the derivative of the outside function. And then, like the chain rule says, we have to multiply times the derivative of the inside function, because y is a function of x. dy dx is the derivative of y with respect to x. Okay, so that's that. What about the derivative of y squared? What's the derivative of y squared?
2y.
To the third. No.
Times dy dx.
Yeah. 2y times dy dx. All right, what about the derivative of negative 5y? Negative 5.
That would be dy dx, so multiplied by it.
Yeah. Yeah, in this case with the negative 5, you can think of the negative 5 hanging around just because of derivative homogeneity, and then we ask, what's the derivative of y with respect to x, dy dx? It's not even so much a chain rule question in this case, you know. This is just saying, what's the derivative of y with respect to x? It is the derivative of y with respect to x. All right, and then x squared, what's the derivative of x squared?
2x.
Yeah. And then what's the derivative of negative 4? 0. So now we've done the implicit differentiation. We just need to solve for dy dx. And so let's factor out the dy dx. And we're left with 3y squared plus 2y minus 5. And then add 2x to both sides. And then lastly, we solve for dy dx by dividing by that big quadratic in y. So we get 2x over 3y squared plus 2y minus 5. So let me plot this on Desmos. By the way, if you're working through your homework, I really hope that you're pausing for a minute long enough to graph any functions that show up in your homework on Desmos.com. I think it's something that every student takes for granted, but like the more experience you have plotting things on Desmos, it's gonna be like you learn by osmosis, you know. Like if you want like a easy hack for getting smarter immediately, just get used to plotting things on Desmos. The more you look at it, the better you're gonna get. It's just there's a lot of products that people sell online that are like, you know, get fit quickly, you know, like wear this sauna belt or whatever, and it's going to heat up your belly and it's going to make you lose fat or whatever. And of course they don't work, but everybody's looking for a quick fix to get in shape or get smarter or whatever. This is your quick fix for getting smarter. Graph every single function you see on your homework on Desmos. Obviously work the homework problems too. That's really important. But if you see, you know, what you're doing, I think it adds a lot of character to it. Remember that the slope of the curve is the derivative and blah, blah, blah. So this red curve is not a function, right? It's not a function because it fails the vertical line test. If I choose x equals 2, then there's 3 different y values corresponding to that input value. There would be this one, and this one. So it is not a function. This is just an implicitly defined curve. But we can still find the slope of this curve if you choose any point and plug it into our derivative equation. Like maybe you want to know what's the slope of my curve at x equals 2, y equals 0, because that's a point right here. Well, then you could just plug in x equals 2, y equals 0, and that would give me 4 over 5, well, 4 over negative 5. So it'd be negative 4 over 5 at the point 2 comma 0. And then we look, does that look like a slope of negative 4/5 right here? Yeah, kind of looks like negative 4/5. And that's really what I mean when I say like graph everything on Desmos. What I mean is like work the homework problem and then graph it on Desmos and then think to yourself, does the actual picture I'm looking at verify what I discovered with my pencil and paper? Does it match up? Okay. Exercise number 2. Find the value of dy dx where x is equal to the square root of 2 and y is equal to, you know what, let's pretend we don't have the y value. Let's pretend this problem is a little bit harder and we're not actually given what the y value is. And we'll talk about how to do it. Okay. If I'm trying to find dy dx, I need to take the derivative with respect to x of both sides of this equation. And so on the left side, what's the derivative of x squared? 2x. What's the derivative of 4y squared?
8y times dy dx.
Perfect. 8y dy dx. What's the derivative of 4? 0. So we've done now implicit differentiation. We just got to rearrange this with our algebra skills. Solve for dy dx. And that means I'm going to subtract 2x from both sides and then divide both sides by 8y. And what do I get?
Negative 140.
So now my dy dx depends on what the x value is and what the y value is where I'm trying to evaluate this derivative. So I've got to go back to this original equation that we started with. X squared plus 4y squared equals 4. And plug in x equals square root of 2. The square root of 2 squared is 2. Subtract 2 from both sides. Divide both sides by 4. Take the square root of both sides. And there's 2 possible y values. Y could either be positive 1 over square root 2 or negative 1 over square root 2, corresponding to this x value of square root 2. So that means I'm going to get 2 different derivatives depending on which y value I choose. So where y is equal to positive 1 over square root 2, my derivative is going to be negative square root 2, because that's my x value, divided by 4 over square root of 2, or 4 times 1 over square root of 2. I'm kind of simplifying as I go. And then dividing by a fraction is the same thing as multiplying by the reciprocal. And so when I have this, that's the same thing as negative 2 over 4, and that is negative 1/2. So where y is equal to the positive 1 over square root of 2, the derivative is going to be negative 1/2. On the other hand, what if I choose the point where y is equal to negative 1 over square root of 2? Well, everything about the derivative would be the same x value, same y value, but it's negative. So I'm just going to make this dy dx a positive half, rather than going through all the same work. Just now I flipped the positive or negative sign. So I got a different slope depending on where I am on the curve. Again, always do this. Always just, now that I've solved the problem, get on Desmos and we'll graph x squared plus 4y squared equals 4. And here is the line where x is equal to the square root of 2. And sure enough, where x is equal to the square root of 2, there's two possible y values. Y is either positive, what is that? 1 over square root 2? Yeah. Or negative 1 over square root of 2. And if I choose the positive y value, then the slope is negative half. And if I choose the negative y value, then the slope is positive 1/2, right there. Sounds good? Okay. All right, find the slope-intercept form of the tangent line to the curve where blah, blah, blah. Okay. If I see this, the first thing that I'm doing is distributing that x squared. This is a good problem. Because now I need to take the derivative with respect to x of every term in this equation. And so what's the derivative of x to the 4th power? 4x cubed. What's the derivative of x squared times y squared?
2xy squared plus x squared 2y. You do the product rule?
It is the product rule. And Gabe almost got it exactly. So the product rule is, yeah, exactly. The product rule is this. If I've got an f and a g and I'm multiplying them together, then the derivative of a product is f prime g plus fg prime. So this is going to be 2x times y squared plus x squared times 2y dy dx. And then what's the derivative of y squared? 2y. Ooh, are you forgetting something? dy dx. Yep. Yeah, so when we look at x squared times y squared, we think product rule. That's perfect. Again, I wrote down the product rule formula, so I didn't make any mistakes. I want to be really careful. The derivative of x squared is 2x. We multiply times y squared. We do not put a dy dx, right, on that term because we haven't taken the derivative of y. For the next one, we say plus x squared times g prime. So we're talking now about the derivative of y squared, which is 2 times y times dy dx. Because we got to use the chain rule. We got to multiply it by the derivative of the inside function. And the inside function there is y. The derivative of y is dy dx. Make sense? Okay, so now we got to solve for dy dx, and so now take your equation and let's subtract from both sides the 2x squared y dy dx. And then we're going to factor out the dy dx. And we're left with 2y minus 2x squared y. And then we just divide everything by that parentheses factor. I could also look at the left side of this equation and how do I simplify that a little bit more?
Divide by 2.
Yeah, I can divide the numerator and denominator by 2. So that means that 2 goes away, that 2 goes away, that 2 goes away, and that 4 becomes 2. Because I'm dividing the top and bottom by 2. So that's part of it. We just found dy dx. The next thing I need is to figure out what is dy dx at these given points, where x is equal to square root 2 over 2 and y is equal to square root 2 over 2. So let's proceed with that. And see what we get. Two times square root 2 over 2 cube is going to be, I think, square root 2 over 2. And then x times y squared is going to be the same thing as square root 2 over 2 cubed, because x and y are the same number right now. And so think about square root 2 over 2 cubed. There's going to be 3 copies of square root 2 in the numerator, 3 copies of 2 in the denominator. I think it's going to be square root 2 over 4 when you're done simplifying. Divided by y, which is square root 2 over 2, minus the same thing, because remember x and y are both square root 2 over 2, so this is square root 2 over 2 to the third power. We've already done that one, so we can subtract that thing. And that means we're going to have 3 times square root 2 over 4 in the numerator, and in the denominator, 1 times square root 2 over 4. When we're done adding and subtracting, dividing is the same thing as multiplying by the reciprocal. So imagine multiplying by the reciprocal and the 4's cancel and the square root 2's cancel. And I think the slope is 3 there. Huh?
I'm confused how you got 3.
Right here. So this is a half plus a fourth, and you get 3/4. Yeah.
Okay, I see. Thank you.
So you plugged it into the equation that we just got for dy over dx.
Yeah. I plugged these values for x and y into this equation. Boop. And I was also simplifying, yeah, as I went along. Yeah. I think, most like 8th or ninth grade math teachers will try to teach you how to rationalize the denominator and simplify square roots and things like that. And then you forget it because you don't practice it for a while. But that's exactly the skills that I'm using right here to find out the slope is 3 at that point. So we're like almost done with the problem. Let's go back and check what we need. We need the slope-intercept form of the tangent line. And to start off, even though my goal here is the slope-intercept form, I'm still going to start with the point-slope form. Well, what should my x and y values be? I could use these for the point. These are going to be my x and y values that I use here. And then for the slope, I've got my slope. So let's do y minus square root 2 over 2 equals 3 times x minus square root 2 over 2. And then we get 3x minus, oh, that's supposed to be a 2. 3x minus 3 square root 2 over 2 plus 2 square root 2 over 2. So y equals 3x minus 2 square root 2 over 2, so minus square root 2. That's my tangent line. Okay, it's time for some Desmos. We're going to plug in the original equation, x squared times x squared plus y squared equals y squared, and see what we get. That's my original curve, defined implicitly. And we are concerned about the point where x and y are the square root 2 over 2. So that's the point here in blue that we care about. And let's see if we got the tangent line correct. So y equals 3x plus square root of 2. Minus square root of 2, sorry, 3x minus square root of 2. There we go. That's good. Looks like the tangent line. Questions? Thoughts? Concerns? So we've done tangent lines before. We did that even before our first test. You know how to take derivatives. Really, the new thing today is like what we did here in orange. That's the hard part to think about. Does everyone feel comfortable with this idea, though, that like... Okay, good. So I'm out of lecture notes. If we still have time in class. What I'd like you to do is take a look at your homework page that I handed out. Everyone got a homework page, I hope. Do you see any problems on the homework page you'd like to work together?
The tangent pi over 6x plus tangent pi over 6y equals xy.
Okay, sure. that could be a fun little exercise. We've got tangent of pi over 6x plus tangent of pi over 6y equals x times y.
Yep.
And let's start by finding dy dx. And we're going to do so by taking the whole equation and taking the derivative with respect to x. So what's the derivative of tangent?
Secant squared.
Yeah. The derivative of tangent is secant squared and the chain rule, so they have to multiply by pi over 6. Now, we just said the derivative of tangent was secant squared, so I should also do the same thing here for this tangent. This tangent gets to become secant squared. Pi over 6y. But the chain rule says I should multiply by pi over 6 and dy dx. Thank you. Okay, the right side of the equation. What's the derivative of x times y?
dy over dx.
Okay, so let's talk about...
y plus x to dx.
This is going to be the product rule, remember? We've got x times y. So think about the derivative of x times y plus x times the derivative of y. This is the derivative product rule in action. So we've got y plus x dy dx. Okay. Now we've done the differentiation, we just need to solve for dy dx. And so maybe what I do is I say we'll start with pi over 6 secant squared of pi over 6 x minus y. I'll go ahead and subtract y from both sides. It has to be equal to dy dx times x minus pi over 6 secant squared pi over 6y. So that in this step, we went ahead and subtracted this free floater y from both sides. And I had an x on the right-hand side. I also subtracted this part, the pi over 6 secant squared blah, 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 on the right-hand side. So like it moves over and becomes negative to the right side when we subtract that from both sides. And then the last thing I did is I went ahead and factored out the dy dx. Because both of these terms had a dy dx, I went ahead and factored that out. So when you're feeling good about that, divide both sides by everything in parentheses there. And we will get pi over 6 secant squared of pi over 6 x minus y, all divided by x minus pi over 6 secant squared of pi over 6y. There's more to do, right? We can always plug in values for x and y and find tangent lines and stuff. But let me pause really quick to make sure everybody catches up on your notes. Everyone has a chance to ask a question if you have a question.
Will there ever be a time where it's like d over like respect to y instead of x?
I guess you could do that, but it's exactly the same procedure. You just swap the x and the y's.
Know, like on the test,
Yeah.
something like that.
No, I'm not going to do that on a test. No, but just remember that the way you label the variables is completely arbitrary. So if you were asked for dx over dy, you could just literally just change the x's for y's and the y's for x's everywhere you see an x and a y, and then you can work the problem and solve for dy dx, right? So it's totally fine to do that. Okay, so what you might want to do next, I don't know, is you might want to say choose x equals 1 and see what happens. And so I would take my original equation here in blue and plug in x equals 1, and we'll see. That one I would have tangent of pi over 6 plus tangent of pi over 6y is equal to y. The tangent of pi over 6 might be a little bit tricky to think about, but remember that tangent is sine divided by cosine. And I remember from my unit circle that sine of pi over 6 is a 30, 60, 90 right triangle, and sine is opposite over hypotenuse, so it's 1/2. And cosine of pi over 6 is the square root 3 over 2. And dividing is the same thing as multiplying by the reciprocal. And so tangent of pi over 6 is going to be 1 divided by square root of 3. So this equation becomes 1 over square root 3 plus tangent of pi over 6y is equal to y. That's a hard question. Yeah. I didn't really check this problem out when I was writing your homework. I've got to work kind of quickly in order to prepare for all my classes, and so I didn't work this problem out by hand. I think the reality is, if I give you this question on a test, I'm only going to ask this question in the context of like exercise 1. Like, I could realistically ask you to find this, but you know, if I only gave you an x value, I wouldn't be able to expect you to find a corresponding y value. There is a corresponding y value, it would just be hard to find.